We reporting to you on hot topics of today's news science. We are presenting to you preliminary chain
reaction. My name is Dominica Anamalachi.
My name is Muslim Maxwell.
PCR. We chose this topic because the technique of PCR has made it possible to analyze DNA fragments and samples that contain amounts of DNA that is either too small or too degraded to permit other types of standard nucleic acid analysis. As a result, it now becomes possible to characterize DNA fragments found in many quantities in places like blood, semen, or hair crime scenes or cells from extinct animals. The birth of PCR. PCR process was conceived in 1983 on U.S. Route 101 in Northern California. Kerry Mullins, a scientist working on Celsius Corporation, was struggling to devise a sample method for determining the identity for a specific nucleotide along stretch of DNA. PCR was introduced to scientific committee in October of 1985. In 1990, Science magazine named PCR the reaction of the year. By 1994, over 15,000 papers have been published on the use of PCR technology, and it is estimated that PCR articles are currently being published at the rate of over 500 per month.
Early dilemmas and resolutions. When first developed, multiple cycles of PCR process were cumbersome for two reasons. Here are two reasons. DNA preliminaries available at the time were heat liable. Manual movements of tubes from the temperature to another.
Two developments was instrumental in the maturation of PCR process: purification and application of heat-stable DNA polymerase, a thermophilic bacterium that resides in hot springs where temperatures can exceed 80 Celsius or 176 Fahrenheit. Automation, which is the invention of thermocycler.
Thermocyclers. Here are four variants of thermocyclers. The first one being DNA thermocycler. The second one, light cycler 480 Rauch Applied Science. Third is MJ Research Doll thermocycler with doll alpha blocks. Last but least, we have ABI 9700 thermocycler. And these are
thermocyclers. Currently in labs today, the thermocycle that's being used is the ABI 9700. At the bottom, the two samples you see is PCR that has been ran through the thermocycler, and here are two samples of them.
Outlines of the PCR process. Initial denaturation. Here are some of the topics that follows under initial denaturation. First one being denaturation. Second, primary annealing. Third, primer extension. Fourth, final extension. Fifth, temperature hold. And these are outlines of the PCR process.
Dissection of PCR process. Initial denaturation precedes the first cycle of reaction. The duration of the step is dictated by the source of the template DNA and choice of thermostable polymerase, usually 2 to 5 minutes at 94 to 95 Celsius. Is adequate to fully denature most template DNAs, including genomic DNAs.
Denaturation typically carried out at 94 through 95 Celsius for 10 to 30 seconds, adapted for the tubes and thermocyclers being used due to exponential natures of PCR reactions. With each cycle, the population of target molecules is doubling. Therefore, there is an increase in short target molecules that are more rapidly denatured in sequenced cycles.
Primer annealing. For most purposes, annealing temperature has to be determined empirically. The choice of primer annealing temperature is probably the most critical factor in designing a high specific PCR. Temperature. Too high, no annealing. Too low, you get dramatic increase in non-specific annealing.
Primer extension, normally carried out at 68 to 72 Celsius. 72 Celsius being optimal for tagged DNA polymerase. Tagged DNA polymerase can add 72 base pairs per second at 72 Celsius.
Final extension. Final extension step is 5 to 10 minutes in common places following the final cycle, which also promotes completion of partially extended products.
Oligonucleotide selection guidelines for primer designs and usage. The goal of most PCR reaction is the amplification of one specific target region. The choice of oligonucleotide primer and their usage is paramount to your success. Success.
Primer length and TM. Typical length is 18 to 30 bases. TM, melting temperature. Manual method of TM calculation are as follows. For primers equal to 20B or less, 4 degrees multiply G plus C plus 2 degrees multiply A plus T. For primers longer than 20B, 59.9 plus 41 times the percentage of G times C minus 600 divided by the length. Other methods include the nearest neighbor analysis. Calculate the TM based on the final salt concentration of 50 mm, or whatever the final ionic concentration. Design forward and reverse primers with similar TM values. Anneal at TM negative 5 degrees Celsius.
Base compositions. Design primers with nearly equal representation of all 4 bases. Avoid long stretches of a single nucleotide. Avoid having complementary base at the 3' which results in primers.
Dimers. Forward primers at the 5' end, you will have this. Reverse primer at the 3' end, you will have this. Your final product will be what you see at the bottom in the green. Aim for a GC content of 50 to 60%. Check for secondary structures formation. Ensure that individual primers cannot undergo intramolecular hydrogen bonding from hairpin structures, such as what you see at the bottom.
Base compositions continue. Eliminate mismatch between the primers and templates in the 3 bases of the primer 3N. The very last 3' base of the primer must hydrogen bond to the 5' base in the template, otherwise the thermostable polymerase cannot extend the primers. Introduce mismatch into the 5' end or preferable middle of the primer. Consult computer software or internet sites for assistance in primer designs and applications. Last but least, analyze the primer sequence by comparisons with known sequences deposited into a public database.
Some variations